Welcome back to Reconstructing Relativity, Chapter 18 on length contraction or measuring length contraction. If you've been following along with this series already, you already have a pretty good handle on how length contraction happens physically. It's that the energy within all particles in its harmonic cycling pattern has to get shorter in the direction of motion in order to maintain that harmony. So there's no stress or pressure involved. Just naturally, every particle becomes shorter, and so every structure becomes shorter. That means in a real sense, objects occupy fewer Planck lengths of distance in the universe. But if you're in any moving reference frame, you can't notice that because you get shorter in the direction of motion. Every measuring instrument you have gets shorter in the direction of motion, and everything seems completely normal. But we haven't covered measuring of length contraction, and particularly we want to look at how symmetric length contractions are measured. Once again, we need to consider the process of measurement carefully, not just take it for granted. How can you measure the length of something that is moving relative to you? About 30 years ago, I was on a trip around the country and with a sketchbook, no camera. And I was on Lake Michigan, and this long, very long ore ship was coming into harbor. And I tried to draw a picture of it, but it was a challenge because the boat was moving, so I had to sketch real quickly, couldn't get many details, and it was moving past me as I was drawing it. So I had to fake it a little bit. It wasn't too accurate. So here's a picture I found on the internet of the same ship. Somebody else took this photo, and obviously the advantage of a camera is it gets the entire image in a blink of an eye, almost simultaneously. If you get really technical about it, the light coming from the near part of the ship gets to you faster than the light from the far part of the ship. But the light's so fast that that's for the purpose of taking a photograph of a normal object that's slowly moving here on Earth. Camera's perfect. You get into trouble with cameras when you take pictures of things moving really fast, like propeller blades, race cars. But the key is simultaneously. You want to gather all your data at one instant. That's what cameras are all about. But even cameras aren't perfect, as this hilarious photo shows. The distortion in the tires, they are leaning forward because the shutter of the camera, swept from bottom to top, didn't capture the whole image at one time. So even cameras don't really capture simultaneously, and you have to be a little careful with them. But simultaneity is the key to measurement or observation. So how could you measure the length of this long ore ship while it's moving relative to you? You can't get on it and measure it. No, you got to do it from your reference frame. You need your own reference frame. What you need is synchronized clocks in your own reference frame at various positions. Then you can measure the length of this thing. This is how you do it. It's all about simultaneously capturing the position of the bow and the stern of the ship. One clock would measure the exact time when the bow of the ship passed by it. Other clocks would measure the exact time when the stern of the ship passed by them. The distance between that nose clock and the stern clock, which measured the same time of passage, that would be the measured length of the ship. If you digested my twin paradox and other previous videos, it should come as no surprise. In relativity, length contraction is real, but the symmetric measurement of length contraction happens because of time skewing. A V equals 0 reference frame, in other words, a reference frame that happens to be not actually moving through space, will measure the lengths in a moving frame as shorter than their own because they actually are shorter in the state universe sense. They are occupying a shorter distance in terms of Planck lengths. But a moving frame measures lengths in a v=0 frame to be shorter than their own because the moving frame's clocks are skewed. Two reference frames moving relative to each other that are both actually moving through space will both have shorter lengths and will both have time skewing, but they'll measure the same symmetric length contractions if the relative velocities of the frames are the same. So again, Einstein is right. It doesn't matter where the space is, and I'll show a case of both frames actually moving through space to confirm that. But for conceptual clarity, as a starting point, let's again start by comparing a v=0 frame to a moving through space frame, just so we can have a better vision of what's happening. So let's start with this simple case. Two rocket ships, they're identical, they're both built in the same factory, and but they find themselves in space, far away in space, and in actual fact, unbeknownst to either one of them, one ship is not moving through space at all, and the other one is moving through space at our old friend 0.866c. So it's an actual Planck length that's twice as short, and the moving ship has time skewing. So we're gonna represent this ship. All that really matters for the demonstration is we can treat these as stick figures. We're gonna have two ships represented by two sticks and 3 clocks each. So there's a leading clock, a midship clock, and a trailing clock on each ship. And we're going to use this to demonstrate the measurement of lengths. Remember, in actual fact, they're identical ships, but in our state universe view, we can see that one is, if you stopped the universe and looked at it at this particular instant, one ship is actually shorter than the other and has time skewing. The other is its full original length, as let's say as large as it could possibly be, as long as it could be, and has no time skewing. The clocks and the upper ship are not only synchronized in their own reference frame, but they actually read the same time at the same time in the state universe sense. No time skewing up there. So here's a picture. It looks a little complicated at first, but I'll step you through it. These are stick figures of the ships at 4 different, and their relative positions at 4 different instants in state universe. So they start out at the top, and as time progresses, we go down to the next set and the next set. So the first thing we see is at time 0, when their noses first cross, both of the clocks in the ships are at time 0. Okay, now the blue ship is the one that's not moving through space. The brown ship is the one that is moving through space at a v/c of 0.866. So, and the lengths of these ships are, well, as we say, normalized. In other words, the units, the total length of both ships in their own reference frame is 2. For example, we might say each ship is 2 light microseconds in length, and then the times we're showing are microseconds. Okay, so we're just trying to simplify the units, but remember, in those units, the complete length of the ship is 2. The distance from the middle of the ship to either end is 1. So looking at the brown ship, we can see the familiar at the top left. We can see the familiar time skewing, that the clocks that are towards the rear in the brown ship as it moves towards the right are time skewed. Their clocks are set forward by v/c times x, since the x is 1 length unit, the clocks are set forward 0.866 per x. So since it's 1 unit back to the middle of the ship, 0.866 set forward there, another unit back, 1.732 is twice 0.866. The next thing we can notice, as we did in the twin paradox, is that both ships measure each other to be going 0.866c in their reference frames. For example, right here, at this point, the blue ship says that the brown ship has gone 1 unit forward. It's gone half the length of my ship, and it took it 1.155 time units to get there. Well, that's 0.866 is 1 over 1.155. So that's correctly measuring the velocity to that point. Meanwhile, the brown ship says, well, at the same time in state universe, the brown ship sees the tip of the blue ship has traveled twice its full length. It traveled its full length, or 2 units, and the time on its clock says 2.309, which again, 2 over 2.309 is 0.866. So they're both measuring the speed of the other ship by watching the nose as it passes their own clocks. They both measure the speed relative to each other to be 0.866c. And symmetric time dilation? Sure. We can see that too. The blue reference frame, as it watches the clock at the nose of the brown ship, right here it says, well, that clock was reading 0 when mine was 0, but now it's only reading 0.577. My clock is reading twice that much. So the brown clock's going half the speed of my clock. Meanwhile, over here, the brown ship has been watching the clock at the nose of the blue ship and says, well, when we started out, blue's clock was 0. Now it's 1.155, but my clock at that position is 2.309. So that blue clock appears to be going half the rate of the time in my reference frame. And that's how that measurement is made. And so same thing we saw as in the twin paradox, same phenomenon. So for symmetric measurement of length contraction, what we said we had to do with the oar ship, what we had to do is have 2 clocks in our reference frame reading the same time while they're at opposite ends of the other ship. Then we measure the distance between our 2 clocks that are reading the same time, and that is the length of measurement of the other ship. So in the case of the blue ship, it's fairly straightforward. It happens right here. Both clocks on blue are reading 1.155. One clock is at the nose of the brown ship. The other clock is at the tail of the brown ship. So therefore, the blue ship says that's the length. The length of the brown ship is the distance between my 2 clocks, which is half of my ship, which is 1 length unit. So blue says the length of brown is 1, which is half of my length. My length of my ship in my reference frame is 2. So finally, how does the brown ship measure the blue ship to be shorter than itself? Same rule. Brown has to have 2 clocks. One reads a certain time as blue's nose passes it, and another clock on the brown ship has to read the same time as blue's tail passes it. And then brown just has to check the distance in its own reference frame between those 2 clocks. So here's where that happens. Blue's nose clock passes brown's tail clock at 2.309 on brown's clock. And then over here, down here, a later time in state universe, blue's tail clock passes brown's midships clock at the same time, 2.309. Well, now brown just says, okay, so I've got the same time on both clocks for those 2 events, and the distance in my ship, in my reference frame between those 2 clocks is 1 unit, half of my ship. Therefore, I measure By the rules of measurement, I'm measuring the blue ship to be shorter than my own by a factor of 2. And remember that 2, the gamma of 2, goes along with the relative velocity of 0.866 c, and which is what you have when one ship is at v equals 0 and the other is at 0.866 c through space. But there's other ways to have that same relative velocity. So as awkward, you got to remember, as awkward and strange as some of these measurements seem, particularly that last one, length contraction, there's really no way to know if you're the ship that's not moving through space, or you're the ship that is moving through space, or much more likely both ships are moving through space. The same things will happen in each situation. And again, we'll do a case where both ships are moving through space, and it's not so simple. I'm still working on the graphics for it. It's obviously a little more difficult to put it together, but we really need to verify that, we're looking at this special case of v equals 0 just to make it simpler to see how these things play out, where one frame is still in space and the other isn't. But it works in each situation. And Einstein's totally right. Doesn't matter where the space is. Special relativity just depends on the relative velocity between the two ships. So that's it for today. I'll be back with that more complicated case fairly soon, and no doubt some more philosophy talk. Got a few more topics in that regard. But let's leave it on a somber note. The Wreck of the Edmund Fitzgerald by Gordon Lightfoot, in remembrance for the 29 who died in that shipwreck. Catch you next time. Bye.
The ship was the pride of the American side, coming back from some mill in Wisconsin. As the big freighters go, it was bigger than most, with a crew and good captain well seasoned, concluding some terms with a couple of steel firms when they left fully loaded for Cleveland. Then later that night when the ship's bell rang, could it be the north wind they'd been feeling?